Hi, I'm Emily, and I'm going to tell you about quantum computers. Let's break it down. What is a quantum? A quantum is a unit of energy, specifically the smallest discrete unit of energy. For instance, quantized radiation exists as a whole number of quanta. But what does it have to do with computers? An ordinary computer works by manipulating bits, where each bit is either a 0 or a 1. Physically, this translates to the opening and closing of electric circuits on the computer's circuit board. A string of zeros and ones are combined as the input, then processed in an algorithm. A new string of zeros and ones are produced, which instruct the computer as to which circuits to close and which to open. Quantum computers, on the other hand, use a unit called the qubit. A qubit can take one of three states, 0, 1, or a superposition of both. Superposition is when a tiny particle, think electron or photon, takes on mutually exclusive states simultaneously. Interestingly, once observed, the system eliminates all but one possible alternative. This is famously represented by Schrödinger's cat, where a cat is locked in a lead box with a cyanide vial. The scientist has no idea whether the cat lived or died, so while the system remains unobserved, the cat is simultaneously alive and dead. Of course, when the box is opened, it becomes abundantly clear which fate has befallen Fluffy. But if a quantum computer still spits out either 1 or 0 at the end, how is it better than a normal computer, other than sounding cool, of course? By itself, a qubit can exist only in one of these three states. But when it joins other qubits in a system, they experience a phenomenon called entanglement. What this means is that if you look at qubit A entangled with qubit B, and you know A's value, you can determine B's value. This is because when atoms are disturbed, they entangle with each other and adopt the same properties. Left alone, an atom will spin in all directions simultaneously, but once observed, one entangled atom will assume the value 1 and the other 0. Because of this, entanglement is not stringing together all the individual qubits. You have to describe all the correlations between the individual qubits, which grows at a rate of 2 to the n correlations for n qubits. This means that when there's a system of 300 qubits, it has more correlations than atoms in the known universe. Let's say we input 8 values into a normal computer, and we need to know if either half or all of them will be 1s. A regular computer has to look up 5 values. A quantum computer could look up all those values simultaneously. As the number of inputs grow, a standard computer must look up 2 to the n minus 1 plus 1 times, while a quantum computer looks only once. This means that a 30-qubit quantum computer is over 10,000 times faster than even the most efficient digital computer. That seems like the best of both worlds, right? Not exactly. The problem is that a quantum algorithm also outputs in quantum state. What does that mean? It means that once observed, the system changes, so we have to get information from the system without observing it. Because of this, quantum computers are great for tedious tasks, like searching for a single number in a phone book where there's no conceivable pattern and lots of inputs. Quantum computers could be used to crack codes, especially those encrypted with time-consuming functions. They could also be used in the fields of biology, chemistry, and medicine to simulate the quantum behavior of complicated molecules. Currently, the best quantum computer contains 16 qubits and can only solve very simple problems. However, if the number of transistors on a microprocessor doubles every 18 months, within the next 15 years, our transistor will need to be smaller than an atom, and the only place to turn is quantum computing.
Thanks for watching!